It's kind of similar to the BKL you heard about a lot about yesterday. There's this ideas that were introduced by physicists, and it takes 50 or 60 years before mathematicians can get a handle of that. And this is something even older. So that's so Einstein, you all know about. Leopold-Infeld and Bianchi-Hoffmann were two associates of Einstein at the Institute for Advanced Study. And in 1938, they came out with this paper, the gravitational equations and the problem of motion. Then there was a follow-up paper 2 years later without Hoffmann. And the most interesting thing about these papers that they were published in the Annals of Mathematics, published by Princeton University. And even in the 30s, the Annals had the same formidable reputation that it has today. So, and I've been to more than one faculty meeting where the promotion decision of the colleagues depends on how many papers do they have in the Annals. So, and so I looked at the for fun, just what are some other papers that appeared in the same volume. And in 1938, and for example, Bochner has 3 papers in that volume. Erdos is there, Erdos Turan is in the same volume. And Steenrod, MacLean, you know, the papers that sort of breakthroughs in mathematics were being published at the time. And then there is a paper by a prominent physicist known, famous for being bad at mathematics. And so it's very interesting. And of course, Infeld became a professor here in Toronto. So I think and maybe this paper had something to do with that. So anyhow, so what they do in this paper, this is the quote, the first line in the paper. We investigate the fundamentally simple question of the extent to which the relativistic equations of gravitation determine the motion of ponderable bodies. Okay, clearly not a math question. It's a physics question. And what is it that they're talking about? Of course, when they say the relativistic equations of gravitation, we know what they're talking about. That's Einstein's equations, right? They don't have to say that. And what do they mean by determine the motion? And what do they mean by ponderable bodies? What are they talking about? Billiard balls, planets, galaxies? What is that, right? Particles. So the next sentence that I'm going to show you, I think is crucial. It answers all of that questions in a sense. They are really going to tell us what it is mathematically that they are after. So, and so here it is. The ordinary Maxwell, they are giving an example. So the ordinary Maxwell's equations for empty space in which electrical particles are regarded as point singularities of the field, the motion of these singularities is not determined by the linear field equations. On the other hand, the well-known theory of Helmholtz on the motion of vortices in a non-viscous fluid gives an instance where the motion of line singularities is actually determined by partial differential equations alone, which are there nonlinear. Okay, so there's a lot to unpack here. But first of all, here's what they mean by ponderable bodies. Point singularities in the field. That's in their first example. And in the second example are line singularities in another field. So this is what they're going to do. They want to do the same thing with Einstein's equations. They want to take a singularity, assume that you have a solution that has a point singularity, and the claim in this paper is that they can derive the equation of motion for that point singularity from the field equations alone, without assuming any other principle, just from the field equations alone. And the other claim implicit in this is that they can do so because Einstein's equations are nonlinear. And they give the example of Maxwell's equations are linear, and therefore this is not possible. So probably the idea there intuitively could be that if you want interactions, you need nonlinearity. So if you had two waves that wanted to interact and you had a linear equation, they would just, you have superposition, they would go through each other. So you won't, maybe that's what's behind it. Anyhow, what I'm going to show you today is that this claim is false on many, in many ways. In particular, I will show you an example of a linear field equation for electromagnetism, but not Maxwell's original, like an alternative theory of electromagnetism, which is still linear, and in which you can carry out these programs successfully. So what do these guys do in this paper published by the Annals? They take small spheres, this is their idea, take spheres around these point singularities, average some field quantities, relevant quantities on these spheres, and derive ordinary differential equations or some kind of differential equation for the motion of these spheres in this way, take some kind of limit, and so on. So, which is a reasonable thing. And you will see later on, I will probably do also something like that. Except this doesn't work the way they're doing it. So at some point, we see this sentence shows up. It is most convenient to take definite infinitesimally small spheres whose centers are at the singularities. Okay, good. But in this case, infinities of the time the limit as r goes to 0 of constant over r to the n can occur in the values of the partial integrals. These are the integral surface integrals on these spheres, and r is the radius of this sphere. Since these must cancel, this is a quote. Since these must cancel, however, in the final result, we may merely ignore them throughout the calculation of these surface integrals. And all I have to say to that is to paraphrase a famous physicist who said, just because something is infinite doesn't mean that it's zero. So that's, but anyhow, it's published in the Annals. So that's, by the way, there's a postscript to these two papers. 10 years later, they published, this time not in the Annals, in the Canadian Journal of Mathematics, and where they try to correct some of the mistakes in these papers, but still the fundamental objections are not addressed. Okay, so, and of course, a year later, the whole thing with Infeld and Toronto comes to a very bad end, but that's a story for another occasion that you can ask me about. And so now this idea of thinking of matter particles as singularities in the field and in the space-time is an older one. And one of the biggest proponents of this idea was Hermann Weyl. He wrote several papers. The title of one of these papers is Was ist Materie, or What is Matter, right? And and in there it says, he proposes this idea that matter now appears as a real singularity in the field. In the general theory of relativity, the world possesses arbitrarily connectedness. In its topological properties, it can behave like a four-dimensional Euclidean continuum from which different tubes of infinite length are cut off. So this is a quote, and this is in a philosophy paper, so some interpretation is required. These are my two takeaways from this paper. A particle word line is a time-like singularity of a space-time. So this is the kind of singularities that we are talking about. This is the kind of singularities that Einstein-Infeld-Hoffmann were interested in. We are talking about time-like singularities. We are not talking about space-like singularities hidden behind horizons. We are talking about naked singularities. And these singularities are not part of the space-time. They need to be excised. They are like defects. So there's another paper with the same theme. This is the infamous ER paper, which is not equal to EPR. And the title of this paper is The Particle Problem in the General Theory of Relativity, the particle problem. And their idea is Einstein and Rosen try to model a particle, a point, right, by gluing together two copies of exterior Schwarzschilds at their horizons to get a singularity-free solution which is localized, behaves like a particle. So what's interesting in this paper also is that particles can represent bridges connecting two asymptotically flat ends. So, and space, therefore, can be multi-sheeted, like a Riemann surface. So these are kind of ingredients that we've been interested in for a long time. We've been exploring various aspects of it. And today I wanted to tell you a little bit about what we have done in this direction. So let me first start by so this is what I was saying, the new approach that we have. This was started by my colleague, Michael Kissling, and then I joined him later. And the idea to get these equations of motion for the singularities is as follows. Let us assume that you have field equations that are derivable from an action principle. Most fundamental equations of physics indeed are in this category. Now, there's a general principle, is Noether's theorem that you have heard about. If these field equations are derivable from an action principle, then there exists something called the energy momentum stress tensor, which satisfies this equation that the covariant divergence of it vanishes away from singularities. So if these singularities are of the correct class, and this is important, I guess, to this audience, I don't need to explain. When you say that some function is not smooth, you're not saying very much, right? We have seen here this week, we have seen results where something is true with C0, but not C1, or it's true for C1, but not C2, and so on. So there are different kinds of singularities. And there is such a thing, we believe, as the right class, just the right class of singularities, which will allow these energy tensors to be continued into the location of the singularity. And if you can do that, then it's possible to think of a more general total stress energy tensor that contains contributions both from the field and from the singularity, thought of as particle. So there's a regular part to this object, and that's from the field. And then there's a singular part concentrated on the path of the particle, and that's the particle energy tensor. Now, this is a big if, but let's suppose that we can find examples of that. I will show you examples of that. The next big if is if this more general object, which is now a distributional object, if it still satisfies the equation that its divergence is true, is zero, in some weak sense, of course, in the sense of distributions, then this is something that we can work with. So we claim that if you have these two ingredients, if you have this right class of singularities, and if you can somehow claim or postulate even that this object, generalized energy tensor, is divergence free, then you can get an equation of motion for the singularity. And this part is high school physics, because we have action reaction, Newton's third law that you have heard about. We think of this situation where the total momentum of the system is conserved. So any momentum lost by the field is gained by the particle, any momentum lost and the other way around. Therefore, if you are interested in knowing what's the force on the particle exerted by the field, that would be minus the force on the field exerted by the particle. And the force on the field is the derivative of the momentum of the field. And the derivative of the momentum of the field is something that we can find from the field. So that's basically this calculation that I'm showing here. We have the force on the particle, right, is the integral of the divergence minus the integral of the divergence of the field energy tensor, right? And then this you can write, this is a time derivative of the integral of the momentum field density, and then there's the boundary term, just by Stokes' theorem. So here it is, we have a formula for the force on the particle coming from this expression, which is solely in terms of the field. Yes, so I goes 1, 2, 3, right? So, okay, so this seems great. There is a restriction, however, right? So if you can look at this expression, I think you've already spotted this perhaps. We are the momentum density of the field needs to be locally integrable, needs to be integrable in the vicinity of the particle. And this may or may not be true, depends on your theory, right? Depends on your action. So unfortunately for us, this integrability condition fails for Maxwell's equations, for the standard Maxwell's equations in 3 space dimensions. So in standard Maxwell's equations, you have, in Maxwell's equations in general, you have 4 fields, the E, the B, the D, and the H. And now to have a closed system, you need to relate the 2 of them to other 2. And Maxwell, for vacuum, took this relationship to be the simplest imaginable one, which is E equals D and B equals H. This gives rise to the Coulomb potential, and the Coulomb potential in 3 dimensions is too singular. So the momentum of the field, which would be E cross B, is not going to be integrable. It's going to be very far from that. So except for this detail, this program would have worked. So when Einstein-Infeld-Hoffmann are saying in Maxwell's theory, you cannot get an equation of motion for the charged particles, it's not because those equations are linear. It's because of this non-integrability. And in order to convince you of that, let me remind you the fact that the Coulomb potential has this constant over absolute value of x depends on dimension. So if you lower the dimension, this power changes, right? So if you take it in 1 dimension, then instead of constant over absolute value of x, is constant times absolute value of x. So that's not singular anymore. Well, it is still singular because of absolute value, but it doesn't blow up. So in 1 space dimension, you could do this. And let me show you. Of course, you're going to tell me there is no electromagnetism in 1 space. Yes, I know. But we can do something like a mock version of it. I mean, there is electricity. So let's look at this. Let's look at just the wave equation in 1 dimension and put a source, delta source on the right-hand side, concentrated on an unknown trajectory. So here's the field with its singularity. And now for initial data, let's start with what would give rise to the particle just sitting there forever. That's the static solution. And then perturb it by adding these red terms in there, right? So now this is a simple linear field in one space dimension. This problem you can solve, right? But the Q there is unknown, of course. Given any Q, you can find this field. Now, if you could also get an equation of motion for the particle, then you could hope to close the system and show that the joint evolution has a unique solution, right? So in order to get the equation of motion for this, well, we know what to do. We have Newton's laws of motion, right? I need to write down the two equations. The derivative of the position is the velocity. I'm in the relativistic situation, so I have the relativistic formula for the velocity there in terms of momentum. And then the second equation says the derivative of the momentum is the force on the particle. And for this force, I just told you how to find this force, right? That's so in fact, we can go ahead and do this. It comes from conservation of momentum. This was an idea already implicit in Poincaré's old work on electromagnetism when my colleague Michael Kisling came up with it. And we use that. So this is the result with two undergraduates at Rutgers, and that we could find what this force is. This is the force on the particle. It has two terms. One of them you could have guessed looks like the Lorentz force on the particle, and then there's another term. This is the self force. This is the force on the particle, the force that the particle exerts on itself through the field. So that was kind of the missing thing in the calculation. And from this principle, then you can prove that this has a solution, and we're done. So if you want Einstein-Infeld-Hoffmann for the linear wave equation in one dimension is solved. Okay, so but that's of course very, very far from what we actually wanted to do, right? The next step is what can we do in 3 dimensions, right? Let's say for electromagnetism, already we saw there is no hope for the standard electromagnetism, but there are perhaps other things that one can do, right? This problem, the problem inherent in the standard electromagnetism is a well-known problem. It is called the back reaction problem. Some of you may have heard about it. And this is a classical problem, right? And various people try to come up with ways to fix it, right? So you may have heard of nonlinear electrodynamics. For example, the Born-Infeld proposal. Same Infeld. That is one way to solve this issue, right? But that leads to nonlinear equations. So let's see what we have here. Oh, by the way, subject for another talk, we can also contemplate quantum laws of motion for singularities the same way. So in other words, we also throw in a wave function of the particle and study the joint dynamics of all of them. But that's for another talk. So, however, still the question remains. I had this kind of postulates in the beginning that all of this would work if you assume that this generalized energy tensor is divergence-free. But why would it be divergence-free? Where would that come from? Right? So Noether's theorem applies in the smooth situation and so on. But now we are in the distributional setting. It is not clear that this would still be the case. So one has to, you could say that, oh, we just impose it because we know that energy is conserved. But mathematicians would not like that right away. We say that maybe we can derive it from some other principle that we all believe in. And here's one possibility. Maybe gravity can do that. Because suppose we know that Einstein's equations hold, but in this with this generalized energy tensor on the right-hand side. So and if that is the case, right? So then we know that the left-hand side of this equation is divergence-free. That's the Bianchi identities. And that would force the right-hand side to also be divergence-free, which is an argument that you've heard before. There is one tiny problem, because now these are not smooth functions, these are distributions. So is it true that even a metric for which the Einstein tensor is a distribution, would it still satisfy the Bianchi identity in a weak sense? So this is what I would like to tell you a little bit about, right? So we'll call that the weak Bianchi identities. And it would be interesting to figure out under what conditions on a space-time metric will Bianchi identities hold in some weak sense, because that could open the door to getting the Einstein-Infeld-Hoffmann program by finding the equation of motion on the singularities. Okay, so what are these conditions? Here's one simple case where we can give a definitive answer to this. Let's take your space-time to be spherically symmetric and static. Admittedly, a very simple situation. In that case, we have something called the mass function, which you have already seen here. This in the spherically symmetric setting, this would be the same as the Hawking mass. They are the same thing. And and here's one result with Annegret Burtscher and Michael Kisling. The twice contracted weak second Bianchi identity, which I will show you in a second what that looks like, holds in the neighborhood of r equals 0 if this mass function has a particular kind of expansion in R, right? And which of the form some constant, which must be negative, plus some other constant times R. Okay. So in particular, it will hold for negative mass Schwarzschild, because then this function is just a negative constant, right, in that case. So, okay, so I will show you how this is done. It's very simple, but a little bit about this mass function. If this is a function of R in the spherically symmetric situation, if you push R to infinity, this gives you the ADM mass. And if you can go the other way down to 0, if the coordinate R allows you to do that, and if you get a limit, we're going to call that the bare mass of your space-time, right? And so if this number is positive, it's very easy to see that there will be a horizon. So this will correspond to a black hole. It won't be the kind of time-like singularity that you're interested in. So now let's look at, for example, Schwarzschild black hole, where m is just a constant. Negative mass Schwarzschild, m is a negative constant. Reissner-Nordstrom is already interesting, is this function. And as you can see, this bare mass is now negative infinite. As you let R go to 0. This is, of course, in the super extremal case where you have a time-like singularity and you can push R all the way down to 0. So there are also examples of electrovacuum space-times that come from these alternative theories of electromagnetism that I briefly mentioned. And for those, M of R has this form, and you can see that for for many of them, it's possible to achieve what we want for these spacetimes. And these would all of these things will represent a point charge with mass that that the space-time around it has a static, spherically symmetric solution of Einstein-Maxwell equations. So these are cousins of Reissner-Nordstrom, but they are better behaved. They are less singular. So if a Kretschmann scalar for Reissner-Nordstrom blows up like a constant over R to the 8, for these spacetimes, it's like constant over R to the 6. So it's like negative mass Schwarzschild. They have similar blow-up behavior. Okay, so brief thing about second Bianchi identities. This is something that you've all seen in differential geometry. You can contract it once, and then you can contract it twice, and then you get this divergence of the Einstein tensor equal to 0. All of this calculation is good so long as the metric has 3 derivatives. And if you are in the presence of a singularity and the metric doesn't have 3 derivatives, what happens then, right? So can one make sense of this? This is the question that we want to ask. Of course, you know you can multiply by some smooth thing and integrate by parts, right? And if you do that, you will get this this thing here, right? So remember the way. Let's recall the way Hermann Weyl was thinking about these about the space-time, where you have this something that's topologically like R4, but you're cutting out a number of time-like curves or the number of curves from this, and your space-time is actually the exterior of this. So the space-time has a boundary. So imagine performing this integration by parts trick on a manifold with boundary. You're going to get an expression like that you can see. Of course, to make this mathematically precise, one in presence of singularities, one has to make sense of these integrals. Maybe the integral on the left does not exist because it diverges, right? And maybe I cannot really do Stokes' theorem because these boundaries are not codimension 1, right? They're higher codimension. So I have to do some kind of limiting procedure by first turning them into tubes, do my integration by parts, and then squeeze the tubes and so on shot. So there is some work to be done, but if one could make sense of this, then this would be a way to define weak Bianchi identities, identities satisfied in a weak sense. Okay, so all of that leads to the following definition. If you have a manifold with a boundary and you have a metric defined on the interior, right, then the twice contracted second, and I'm only going to consider the twice contracted second Bianchi identity. That's the one that I need. I don't care about the big Bianchi identity, right? So this one will say that it's weakly satisfied if the following integral is finite for every compactly supported vector field. Right? So this is our definition of a weak version of second Bianchi identity. Once this integral is finite, the idea is you're going to write this integral as the limit as epsilon go to 0 of an integral outside the tube, which then they're going to shrink. And then you perform your Stokes theorem and you use the classical Bianchi identity to get rid of the bulk term, and then you just have a boundary term. So then you'll get what I was writing before, but this time it would actually make sense to do it that. Yeah, so so what I'm saying is that in order to get this thing which I had before, right? In order to say that this is equal to that, I need first and foremost the thing on the left to be finite, to be well defined. Well, the claim is if I just have that this is finite, then I'm going to write this as the limit as epsilon goes to 0 of, now I'm going to go blow up my singularities a little bit and then get a boundary term which I can then shrink. Because the problem with this formulation is that this thing on the right-hand side does not make sense necessarily, right? This thing here, because it says integration on the boundary of M, and this may not, if the boundary of them is codimension 3, then what is that? That's so that's why I'm not. That's why this is probably the only thing that makes sense to define it that way. So of course, if the vector field that you have chosen does not intersect the boundary, then this is going to be 0 just by the classical Bianchi. So there's no content here unless your vector fields are not supported away from the boundary, unless they have some non-zero value on the boundary, then this would really be a restriction to saying what this works. Okay, so I will show you examples of how we do this. And we will show you, for example, that for negative mass Schwarzschild, this thing is actually finite. Not only that it's finite, it's just 0 for all vector fields, right? And for super extrema Reisner-Nordstrom, this is infinite, this integral divergence. So there is a sense in which, as in this big sense, weak Bianchi is satisfied for negative mass Schwarzschild, but is not satisfied for Reisner-Nordstrom. And this, by the way, is going to be connected with what I said about Maxwell's equations, because Reisner-Nordstrom is a solution to Einstein-Maxwell. And just as we could not get an equation of motion for point singularities of Maxwell's equations on flat background, we will not also be able to get it in presence of gravity. Gravity does not help in this situation. So that's kind of going into that direction. Of course, this is not a proof, but that goes into that direction. So we have also recently been, and this was all just in the static spherically symmetric context, but we have recently been able to remove the spherical symmetry assumption. So we still need the static for now, but ideally we would like to be able to do this without any symmetry assumptions. But currently we don't know how to do that. Okay, so here's the argument in the static spherically symmetric case. This is very simple. These are the line elements for static spherically symmetric metrics, can always be put in this form with two coefficients, alpha and beta. Now, you can also define a different coordinate system, which corresponds to conformally flat spatial slices. For these spacetimes, this is always possible. And you get two other coefficients here. This power here, 4, is chosen for beauty reasons. And so you have these two functions, phi, so that to avoid ugly powers in the phi later on. So, so you have these two functions, phi and gamma here, right? And you can, it's trivial to find these in terms of the other, in terms of alpha and beta. You can solve that, and then you can see that. So this is the line, this is the kind of line element that we're going to be working with, right? This function phi is going to be 0 at some r equals r naught, some positive value of r, this of rho, sorry, this phi will be 0 of rho, right? So rho equals r naught corresponds, rho equals rho naught corresponds to r equals 0. So in these coordinates, we are looking at the exterior of a cylinder. Because if you think of rho now as the radius of the cylinder, this is a metric defined on R3 minus a ball cross R. And so what we have done with these coordinates we have taken that line singularity at r equals 0 and geometrically blown it up to become a cylinder, right? However, if you take a slice of that, that's going to be a sphere of radius r0 at the boundary, and the intrinsic area of that sphere will be 0. So these are the 0 area spheres that we are going to be talking about. So it turns out that geometers have studied that. So there is something called a 0 area singularity. This was studied for Riemannian manifolds initially by Bray, and he developed a theory for geometric properties of this, including a notion of mass that can be defined for such spacetimes. So this is the Bray's definition of mass for these, and Bray showed that this mass quantity that he can attach to these 0 area singularities in the Riemannian case are actually always negative. So we're going to connect that to our negative bare mass, which allows us to do the weak Bianchi calculation. So that's like kind of connecting various dots here. So here's our theorem. Suppose your manifold, your space-time has that topology. It's R3 minus a ball cross R. And suppose you have this kind of metric on it with the 2 coefficients phi and gamma. And what we're going to assume about phi is that it vanishes at some r equals or rho equals rho naught. Okay, so we're going to assume that these two coefficients, phi and gamma, have certain blow up rates with respect to this coordinate rho naught. And if you make the right assumptions here, then this calculation that I was claiming can be done before can be done. And then it shows you that this integral is not only finite, it's actually going to be 0 for all these space-time. So this is a special case. If you want, this is a stronger version of weak second Bianchi identity because this constant would actually be 0. Okay, so the argument, and then you can connect this to the mass function also. The special case where the 2 coefficients here are the same, right? Well, one is like in Schwarzschild and so on, where GTT and is the inverse of GRR. Then you just have the one function which you can take that to be the mass function. And a consequence of the previous theorem is that if the mass function has this kind of expansion, then the weak second Bianchi identity is satisfied. Both of these results are proven just by integration by parts. The point is we assumed exactly the decay or the blow up rates that we needed in order to the calculation to go through. So there's nothing very deep about it. It's more the question of what are the right conditions that we are going to need. Okay, so let's look at the Reissner-Nordstrom case. That's the mass function of the Reissner-Nordstrom. Clearly, this does not satisfy the conditions that we have, but here's something that does satisfy. So remember Einstein-Infeld-Hoffmann. Hoffmann is also credited for finding a solution of Einstein-Maxwell together with the Born-Infeld law for the electromagnetic vacuum in the static spherical symmetry case. This is called the Hoffmann spacetime. And you can write down the mass function of the Hoffmann metric. And you see that this mass function does satisfy the conditions that we had before. So, and this is even true in more generality. Okay, so a little bit of, this is a side remark. I will just click through it quickly, right, in the interest of time. I've been talking about more general theory of electromagnetism, where the four fields that appear in Maxwell's equations are related by some other relationship than the one that Maxwell assumed. So you can do it in, this is Maxwell's assumed, and if you couple that to gravity, you get Einstein-Maxwell. Maxwell, the second Maxwell, refers to this particular choice for the E and the B. So it sounds like a law firm, but the consequence of that simple choice is that the electric field and the displacement field are both derivative, the gradient of the Coulomb potential, which is very badly singular, and that does not let you to do anything. So these singularities are too strong, the Lorentz force is undefined, the electrostatic energy of the point charge is infinite. The corresponding solution to Einstein's equations with this theory of electromagnetism is Rice-Nordstrom, which I just convinced you is also very bad in this respect. So addition of gravity did not solve anything. It just made things worse in some sense. And now Born's idea was to choose a different relationship between E and D, which sort of mimics the behavior for the relativistic velocity in terms of momentum. And so E remains bounded as D blows up. That was Born's idea. And so if you do this, you will get Maxwell-Born-Infeld equations. And in this theory, point charges have finite total energy. And Hoffmann found the solution for Einstein's equations coupled to this electromagnetic theory. So that's in this theory, the singularity at r equals 0 is identified with the point charge. I showed many years ago that this is the mildest possible singularity that you can get for this class of spacetimes. So everything else will be more singular. And Bianchi, in the sense that we defined it, does hold for these Hoffmann spacetimes. So in theory, it should be possible to carry out the Einstein-Infeld-Hoffmann in this context. However, Born-Infeld theory is a nonlinear theory of electromagnetism, and therefore the progress in this area has been slow. So far, we know that Einstein, Maxwell, Born-Infeld, without any point charges, is well posed, but with point charges, we don't know. So that's in general. So that's something that still requires further progress. I encourage younger people in the audience to start thinking about these things. There's another possibility which you may be less familiar with, and that's the Bob-Lande-Thomas Podolsky electromagnetism. This is a linear theory of electromagnetism, which allows for superposition and so on. So that's good. You have to pay the price somewhere, and the price that they are willing to pay, it's a higher order theory. So the equations are fourth order instead of second order when you put it in terms of the potentials. So, and this is the relationship between E and D and the B and the H. As you can see, the Klein-Gordon operator shows up. So there is some smoothing effects that come from solving the Klein-Gordon in this case. And once again, E remains bounded as D blows up. So this allows you to have point charges in this theory, which will have finite energy. The field momentum is locally integrable. That's good news. That means that our program for finding the force on the particle works. And this is the theorem that we proved. Well, we proved this theorem in 2019, and we are still writing it up 7 years later. It's just that because when you get older, you have many, your energy gets spread over a much wider area and you have many things to do, both of us. But the basic idea is that because this force on the point charge coming from the field is well defined, you can get a joint evolution for the field and the particles to go through, and you have a well-posedness result there. And then recently, another undergraduate was able to do this also in 2 space dimensions, which is simpler. Now it's not hundreds of pages anymore, but you get the same result. And then one of our PhD students was able to couple this to Einstein's equations and find the corresponding to Reissner-Nordstrom for this space-time. And would be interesting to investigate whether the weak Bianchi is satisfied in that context. Its solution is not explicit, so it's harder to verify whether those conditions that I have hold. But in principle, it should be possible. Okay, so how much time? So yeah, I'm almost there. So I just want to talk about some more work in progress that we have done in this direction. So, so we started by talking about the Einstein-Infeld-Hoffmann, let's call it project or proposal, right? And what was it? To take a space-time that has time-like singularities, right? And see if you can prove, you can first of all get an equation of motion for the singularity to come from somewhere. Now, EIH wanted these things to just come just from Einstein's equations. We don't think that's in the cards. However, we have this alternative that if one could also postulate conservation of local conservation laws in the sense that I was talking about, then in certain situations, one should be possible to carry this out even for the gravitational field instead of the, so basically replace the electromagnetic field in everything that I talked about with the gravitational field and try to do the same thing. Of course, Einstein's equations being nonlinear now is not going to be helpful very much. It's actually a hindrance. So, but in 1 + 1 dimension, something can be done. And this is my recently graduated PhD student, Larry Frolov, showed that you have local well-posedness of joint particle metric initial value problem for the 1-dimensional cartoon of Einstein gravity. Of course, there is no Einstein gravity in 1 space dimension, right? And remember, we started by saying Zwa relativistic equations of gravitation, but it is not the case that Einstein was the only one who had such things. Einstein had the best one. There were other people who had relativistic theory of gravitation. For example, Nordstrom had this. And here's Nordstrom's equation. Instead of R mu nu and so on, it's just R, the scalar curvature, equals kappa, coupling constant, times the trace of the energy tensor. So that's, so now you can replace the right-hand side there with the, in this case, if you don't assume any other field, this energy tensor on the right-hand side will only be the one coming from the singularity. So, and then for this one, Larry was able to show that this problem is well posed. So you get a metric, right? And you get an equation of motion for the singularity. There's an additional difficulty, which is very interesting and important to note, because these equations, let me just say that the covariant divergence of the energy tensor vanishes. The covariant divergence contains the metric, of course. Therefore, it has the Christoffel symbols. So if you are in a context where both the T mu nu is a distribution and the Christoffel symbols are also distributions, then what does it mean to multiply these two things? And it turns out that there is a theory for that. It's called the Colombo theory, theory of nonlinear distribution theory. And by going into this framework of nonlinear distribution theory, it is possible to make sense of this object of the divergence of the T mu nu, and that's how he was able to prove this. So this is one very interesting result, which has a lot of potential, I think. And if you are interested in subject, I ask you to invite Larry to come and tell you about it. He got a position at Maryland as a postdoc, so we're very happy about that. And last I want to tell you about is what I mentioned before, that we have been able to extend our result by removing the spherical symmetric assumption and having it just with the static spacetimes. And that's the result. Everything else is the same. And thank you for listening.